folks. Finishing up this lecture, this kind of introductory lecture on spectroscopy. So this one will probably be shorter than the last one. So, and then what's coming next, we're going to talk about rotational spectroscopy, and then vibrational spectroscopy, and then electronic spectroscopy, as you may have guessed from the way I organize the class. So let's keep going with this introductory information, kind of select content from chapter 12 and 13. And what I want to get into is something that I think is really important for applied spectroscopy. So background versus sample spectra, okay? So I'll remind you, I'm actually going to back up just for a second, okay? And I'll remind you of all of these various photophysical processes that are occurring when light interacts with the sample. So we can get reflection. That reflection can be specular or diffuse, depending on the quality of our surface. We can get refraction if the light is passing through multiple different types of media, which it certainly is in spectroscopy, right? It passes through the air, and then it passes through your glass cuvette, and then it passes through the liquid in your cuvette, and then on and out through the other side. We can also get diffraction, right, when there is a small opening. So all of these processes are important to consider, which is precisely why we take a background spectrum and then a sample spectrum, okay? So these are typically referred to as single beam spectra. So whether it's the background or the sample, we call these single beam because colloquially, we're passing one beam at a time. Technically, we're doing a lot more than that. But these are called single beams because we're going to ratio each of these two, excuse me. We're going to ratio each of these two single beam spectra to each other. And here's why. Well, look, when our light comes in and starts interacting with the cuvette, we're going to get specular reflection. We're going to get diffuse reflection. We're going to get refraction coming through the cuvette. And also, all of these processes are going to occur on the other side of the cuvette, okay? And so all of these will contribute to light not making it to our detector, right? If we think about this, right? This is my my incident beam and my transmitted beam, and my transmitted beam won't reflect what has been absorbed. It will just represent what light hasn't made it to the detector, which could be from the absorbance, but it also could be from all of these scattering events, okay? So the way we get around with that is we first record a background. So this will be identical to the sample as much as possible. Okay, so typically if we can, we would want to use the same cuvette. If we can't use the same cuvette because we want to keep running multiple samples, then at the very least we would do some type of study to figure out how different each cuvette is from the next, right? If there's little bad spots in the glass that contribute to scattering, we would want to maybe throw one of those cuvettes out and use a more pristine one, okay? So we want to try to make this as identical to the sample as possible. And so if this were a solution, so let's suppose if the sample were some type of solution, then my background would be the solvent of that solution, and then the only difference between my background and sample would be I will replace my pure solvent with a solution of analyte solutes in that same solvent that I did for the background. So we'll say analyte equals the solute. Okay? And as I often tell my own research students, if you stand on one foot while singing a song in your head while recording the background spectrum, then stand on one foot and sing that same song in your head while recording the sample. Okay? I am a paranoid scientist, and so to really ratio out all of these photophysical effects that can occur, your background and your sample need to be as identical as possible, with the exception, of course, your sample has analyte molecules in them, okay? So for example, in the solvent solution example, we wouldn't want to have blank air in here. We would want to truly have a matching solvent, okay? And so now the way that this works out, right, my transmitted, or my incident beam, excuse me, I keep mixing that up. My incident beam I0 and I0 will be the same if we've done this as identically as possible. And of course, my transmitted beam will not be identical to this. So when I'm ratioing these out, it becomes a ratio of a ratio, right? I take the absorbance spectrum is literally the negative log of now this I, this transmitted beam, to this I naught, okay? Because when we record these single beams, we're technically taking, for absorbance, right, the negative log of, let's see the best way to represent this. So I'll have an I over I naught and an I over I naught, right? And so one of these I naughts will cancel. Okay, so I should have labeled this and thought about this more clearly. But one of these will cancel because it's identical with the other. And so we'll have a true like ratio of ratios. So we will have ratioed out all of those effects, okay? So we can have single beam spectrometers or double beam. Single beam are by far the most common because they're the easiest to construct. And in a single beam spectrometer, right, we'd have a light source with some type of collimator. So that could be a slit like you see right here, or it could be a set of optics that can focus the beam down onto our monochromometer. Okay. Oh, I knew I spelled monochromometer wrong. Oh my gosh, wait, let's see. You guys probably caught me on that. Yes. It's not a chronometer, that's a watch. Duh. I told you guys I couldn't spell. So the collimator or set of optics, right, focus the light on the monochromometer, whatever, the diffraction grating, right? And that diffraction grating might come out divergent. So we'll use another slit to diffract the beam into a nice tight collimated path so that it can pass over our sample and go onto our detector. And so now I know that all of you are familiar with this. When you want to get an actual spectrum, you would first take a single beam of your background, then usually the software records it, stand on one foot, right? Hold your breath, all the other superstitious things. Then you would replace your background cuvette with your sample cuvette, stand on one foot, hold your breath, cross your fingers, right? Do all the stuff. And then your computer system, your detector, will work out that ratio of ratios to give you the true absorbance or transmittance spectra. Okay? So the really fancy spectrometers are double beam instruments, where you will load in your reference, and this says air or cuvette. Cuvette containing the solvent is what I recommend. And then your sample, right? And again, we hope that this reference or this background is as identical as possible to the sample. And so now this is pretty cool. So the setup is almost identical to the single beam, except for now we have here, you can see M1 is a beam splitter, right? So half the light will go down this way and half will go down this way. So the half that goes through the reference will just pass right through what's called this grid mirror. And this grid mirror allows light to pass through from one side, so it's transparent on one side, and it's opaque on the other side, okay? So the light will pass right through the reference and onto the detector. Great. And also, simultaneously, the light will pass through, so it'll go down to this mirror. These are just ordinary reflecting mirrors, and so that'll pass through the sample. And then, of course, your software, right, the computer program will work out this absorbance spectra for you. And of course, that being said, if this is a dispersion technique, which this definitely is, so I'll make sure that we note that this is dispersion spectroscopy, right? Because we're using a grating. So these things, right, will scan one wavelength at a time, okay? And whether that be from angling the diffraction grating or angling the light source, or what I didn't talk about last time, we are getting to the point where we have more sophisticated detectors that can discriminate wavelengths of light. But those types of detectors still aren't nearly as good at resolving different wavelengths of light as changing the angle of our diffraction grating, okay? So if you have a double beam instrument, these things are great. These things are very easy to use. You typically don't have as much background sample issues, right? If your background and sample weren't identical, with the exception of the analyte molecules, then you have less of those issues with the double beam instrument, okay?